Welcome back to ECE 441A, 541A. I see that our poles are all in the right half plane, or the students are in the right half plane, the way that I see the S plane. Everything is coming to a close, but there's a lot to happen before we finish. Homework 8 is due today. Lab 3 and the project are due Wednesday, as are 2 other homework assignments, 9 and 10. Teacher course evaluations are due Wednesday, and there's additional material on Bodie plots that's on the D2L website. The final exam is a week from Wednesday, and it will be in this room at 8 o'clock until 10 a.m., and that's on the 17th of December. Today what I want to do is continue with Chapter 11 material, which is full state feedback design, and we did an example of that. We went through the theory, then we found with an example the feedback gain elements in our full state feedback matrix K, which was this short wide matrix, but we didn't have time to go through how do we pick in, which scales or weights the reference input as it's injected into the system, and that's what we want to talk about today. We want to determine how do we adjust the reference input gain, and we will see that we really want to adjust that value in such that we have the appropriate gain between the reference input and the output. In particular, well, if we go back, if we have one input to the system, U of t is 1, and we have one reference input, what are the dimensions on this matrix capital N? Just to get us sort of thinking about what we are designing or hope to design with capital N. What are the dimensions on this matrix N? If we have one input, U, and we have one reference input, how big is N? It's 1 by 1. It's a scalar. It's a matrix that's 1 by 1. Capital N is just a scalar. We want to know what value do we pick for that scalar so that we have the right amplification or gain between the reference input and the output Y. And that's what we are going to talk about in the first part of today's class. The K matrix was what dimension? If X is a state that's, let's say 10, let's say we have 10 state variables in our state vector X, and we have 2 inputs in our system U, what is the K matrix? It's 2 by 10. It's not a 2 by 4, it's a 2 by 10. If we were at Home Depot, we could go ask for a K matrix that's a 2 by 10, and I don't know what aisle that's located in, but maybe we could find, no, you won't find that there, but you will find it here. And in our particular example that we were working through, we had a one input, U, and we had 2 state variables, x sub 1 and x sub 2. Our K matrix there was 1 by 2. After we've gone through how we pick our reference input gain, capital N, we will work through a comparison. We will compare what we can obtain with output feedback-based controllers. Those were the G sub C of S's that we were dealing with. We were designing phase lead, phase lag, PID. Those were in that forward path of our system with a unity output feedback. Let's compare that design with these full state feedback control designs. That's what we want to do in the second half of today's class. So let's now talk about incorporating a reference input with full state feedback. And in particular, let's look at this by means of a diagram or a block diagram. Suppose that now that block, let's just assume that that's a bank of integrators. If we have two states, we now have two integrators. And let's say that this is our derivative x dot. Then if we differentiate, or if we integrate each of those state variable components, that will produce x of t. Then our system dynamics are governed by x dot is equal to ax plus bu. If it's ax, then we have this matrix A that will then direct each of these vector coordinates of x into the appropriate location for, let's say, x1 dot, x2 dot, x3 dot, but we're doing this now in a matrix vector diagram. This integrator, again, is a bank of integrators. In our system, it might be a bank of two. There's x dot is equal to ax. There's plus b u of t. That's now our dynamics. We might actually want to measure a linear combination of our states to produce an output y of t. And that now is x dot equal ax plus bu, y is equal to cx. That's our state space representation in a block diagram description, in a very concise block diagram. What we want to do is we want to incorporate this full state feedback, which is minus kx of t plus n r of t, which means that that's going to come in over here. We now need to find u of t, or define u of t, on the left-hand side. It's going to take the state vector x, linearly combine those state vectors by means of this feedback gain matrix, capital K. There is now our minus kx of t for u. And then we have n r of t. And that's now our state space, full state feedback diagram, block diagram, with a reference input, r of t, that we can now tell or command the system to move according to however we want it to be directed. Where this piece of our input is the full state feedback, and this piece is our reference input. If this is our system, and this now is a closed loop system just like we've had before, but now our controller, in a sense, is in the feedback path, but we're now weighting all of those state variables x. We're not measuring, we're not feeding back the output. We're actually going into the system and assuming that we can measure all of the state variables, positions, velocities, voltages, currents, temperatures, pressures, whatever those are, and weight those according to K and feed those back into U. This is a different configuration than what we did earlier when we were designing controllers and only measuring the output Y and feeding that back, and our controller was sitting in front of the plant And now our controller is basically this weighting of state variables through this gain matrix K. What we want to do now is have a particular behavior between the reference input R of t and the output Y of t. Meaning if I command R to go to 10 degrees, if I say R, go to 10, then I probably am wanting my output Y to go to 10. It'd be nice if when I command R, input a step and say go to 10, or in the lab, go to 2000, you're really expecting your Y to go to 2000. Which means what kind of a gain do you want at low frequencies to occur between the input R and the output Y? You want a gain of 1, don't you? So that's one of our goals with this particular design process. We pick K to place our closed loop poles to give us the speed that we want, but now we also want, in terms of the transient, we also want Y of t to track or follow the reference input R of t, which means then that we want a DC gain of 1 between the reference input in the frequency domain R of S and the output Y of S. Or now we really are wanting the transfer function between R of S and Y of S. Now we need to basically take this into the frequency domain and try to find our transfer function for this system. Let's now find then the closed loop transfer function for this system. If we looked at the block diagram, we can basically write our equations down by just inspecting this block diagram, meaning x dot is a x of t plus b u of t. We know that by that block diagram. The output of that middle summing junction is just equal to the inputs. That's a x of t plus b u of t. But we've also told u of t, and we know what y is. We know that y of t is equal to c x of t. Here are the dynamics. Here is our output. And together, this is our open loop system. We've now decided that we want to modify the dynamics of our system by introducing full state feedback, where now u of t is minus kx of t plus n r of t. If we combine the u or replace the u into the u of t in the first equation, we can now start to close the loop. We can now end up with x dot of t is equal to a x of t plus b times minus kx of t plus n r of t. If we now combine the terms that are associated with the different vectors, x and r, we have a minus bk times x of t plus b in r of t, and that equals x dot of t. And I might, just for ease of writing some of these equations, I might just refer to A minus BK as a new matrix F. And we were interested in picking the eigenvalues of F to produce the appropriate dynamics that we want. Now, this is a time domain expression for our closed loop system. We still have in this an output equation, y is equal to cx of t, but now this is our closed loop system using full state feedback. We want to get a transfer function. As a review for the final, how would we find the transfer function if we're given a system of differential equations? Which is what we have here. We have x1 dot is equal to something, x2 dot is equal to something. You could sketch the block diagram and use Mason's gain and find the transfer function. Let's find it algebraically in terms of these variables, a, b, k, b, n, and c. Let's now go into the frequency domain. If we Laplace transform a derivative, and if we're interested in the transfer function, we don't need to keep track of initial conditions, so that now we have s times x of s equaling f, capital X of s, plus b in r of s. And as we have learned, we can insert this placeholder, this identity matrix, because S is just a scalar, and we want to combine this Laplace transform of our state vector, capital X of S, on both sides, and we can't do that by combining a scalar with a matrix F, but we can do it if we have this placeholder I. So that now we can write Si minus F times X of S is equal to B in R of S. If we solve that for X of S by inverting Si minus F, we now have this relationship between the reference input R in the frequency domain and our state vector X in the frequency domain. And that's simply Si minus F inverse times Bn. But we want the transfer function between the input, reference input, and the output Y. We know what Y is. Y of S is simply algebraically related to X of S through the output matrix C, which now allows us to say, oh, we have X of S in terms of R of S. Let's just replace it. This now, as an expression, is our closed loop transfer function. And to give us something to talk about, I might just call that T sub C of S. Transfer function closed loop. Now, if you remember from last time, we had this example that we had found the K matrix, so we had actually found the F matrix. Our example was a second order system. it was x dot is equal to 0, 1, 0, minus 1 x plus b, which was 0, 1 u. Y was just taking the first component of our two-dimensional state vector x, and if u of t was using full state feedback, we had this as minus k x of t plus n r of t, and we had already found k to be 50, 14, we hadn't yet determined what this n matrix was equal to. But last time we picked the K matrix K to produce closed loop poles at minus 5 and minus 10. And that's what generated this value of 50 and 14 in our full state feedback gain matrix. If we now use these matrices, these particular matrices, in this formula, C times SI minus F inverse B, N, you told me if it's relating a one-dimensional input U to a one-dimensional reference input R, capital N is a one-by-one matrix. It's a scalar. Everything else in that expression we now know. We know C, we know F, and we know capital B. We can find that expression, and if we do, we end up with T sub C of S is equal to 1 over S squared plus 15S plus 50. The only thing we don't know is this N. But this particular closed loop system was designed to have closed loop poles at S equal minus 5 and S equal minus 10. And if you examine the roots of S squared plus 15S plus 50, you will see that those give you values of S equal to minus 5 and minus 10. But this right here is simply this C times SI minus F inverse B, where F is A minus BK. That's all we've done to generate that expression in parentheses. We said that we want the output to actually track the reference input, and that said that we wanted this transfer function, T sub C of S, to have a certain behavior at low frequencies, or in fact a DC gain of 1. Let's now make that happen. We know what T sub C is. The only unknown is this scalar quantity capital N. We now want a DC gain of 1. In that transfer function, we have T sub C of S. DC will be accomplished with S equal to 0, or we want T sub C of 0 to be equal to 1. Plugging S equal to 0 in that expression, we now have 1 over 0 squared plus 15 times 0 plus 50 times N is equal to 1. Or that says that we have N over 50 equal to 1. Or now we found a value of N that will give us a DC gain of 1 in our closed loop system, which says if we are applying full state feedback with a reference input, we now know how to pick N to give us 0 tracking error between the reference input and the output Y. or if you really wanted to see how you are combining all of these pieces to form an input signal u of t, you would simply scale x sub 1 by 50, subtract that in the summing junction, take x sub 2, scale that by 14, take the reference input and weight that by 50, and all of that will produce the input u that drives the system in your system. And that will achieve the behavior that you want in this particular block diagram that we started with. We started with A and B and C known. That was our open loop system indicated in black. We picked K to give us the speed or the dynamics that we wanted in our full state feedback design. And then we just now found N to give us the appropriate gain between the reference input R and the output Y. Let's go through a comparison now of doing a design like this with what we've already designed earlier in the semester with transfer function-based controllers. Let's see what those now look like. Now what we want to do is, via an example, let's now compare, or this example will be comparing the output feedback based controllers, which we were labeling as G sub C of S's, with full state feedback control. And now I've just gone back a few decades. I'm now 2 years old, several decades. And somebody says, well, that's not a fair comparison. Comparing this G sub C of S with the full state feedback, and now I ask you guys, why? Why is that not a fair comparison? Even though we're going to do it, what do you have to keep in mind that may be distinguishing these two types of control? We're now looking at output feedback, that's these G sub C of S's, with full state feedback. What's the difference between those two classes of controllers? Do you remember what we talked about before? In this particular approach, we were assuming we could go internal to our system and pull off each one of these state variables, x, x1, x2, position, velocity, voltage, current. In the earlier controllers, we were just saying, oh, you just have the output y. Maybe that's the position of your system. And then you filter that with the G sub C of S to try to get what you want. But now we're assuming with full state feedback that we can go in and we can get all of these states and gain them up and feed them back. But let's now look at how we could basically design these two types of controllers to maybe yield the same behavior, but just keep in mind that you're really doing two different things, or you're sort of assuming you have two different situations or scenarios. Let's go ahead and use the same system that we've been playing with. Oops. So now your state variables, the question is, your state variables would be as simple as measuring your position and velocity. But now let's say you have an engine, and maybe one of your states that governs the dynamics of this mechanical engine is the temperature inside a cylinder. And maybe you can't design, maybe you don't want to spend the money to get a sensor for that. Or maybe you don't want to measure the velocity of something. Maybe you just assume, well, I'll do some filtering and come up with an estimate of the velocity. You maybe don't want to have all of these different sensors on your system to produce the ability to have a full state feedback design. But it's possible. You might be able to measure all of your voltages, currents, positions, velocities, temperatures, pressures, but that's what you're assuming you have available to you. And in a real system, you may not have all of those. Does that answer your question? But yes, in this class, it's trivial. We have x1, x2, x3, x4. In this example, we simply have x sub 1 and x sub 2. Here are the design specifications for this comparison. Suppose now that one of these design specs is to have a steady state error due to a unit step. We want that to be 0. Maybe another design specification is to have a settling time of about 1 second. Maybe a third design spec is to have a percent overshoot of about 5%. We now have 3 different design specifications, and we want to see, is it possible to achieve those 3 design specifications using 2 different controllers? A frequency domain-based controller, maybe we'll design it using root locus since we have these time domain parameter specifications, and full state feedback. Based on these design specs, can you already see in your mind where you want your closed loop poles? And this is now another idealization. We're assuming that we have a pure 2-pole system. Our settling time specification, T sub s, we wanted that to be 1 second, but what do we know relative to system parameters our settling time is? Our 2% settling time is how many time constants? 4. So it's now 4 tau, which is reciprocally related to the real part of our closed loop poles for a 2-pole ideal system, and we wanted that to be 1. So now we know that we want our poles to have a real part in the left half plane of -4 if we have 2 of those. The percent overshoot specification, which we said let's make that about 5%, you now know from figure 5.8 or from the formula, from your experience in this class, what's that mean relative to zeta, a 5% overshoot? What's the damping ratio for a pure 2-pole system? That's the 0.7, isn't it? Which gives us then an angle. If we had complex poles, we want that angle for a 5% overshoot to be the inverse cosine of 0.7, or an angle of 45 degrees. We now need a real part of 4. We want the angle to be 45. That now tells us where we want our dominant poles. We want them at -4 plus and minus J4. That's a final exam review, right? just with those two design specs, percent overshoot and settling time, you can now say, oh, you should have dominant closed loop poles for a pure two-pole system at -4 plus and minus J4, and move on to the next question. But on the final, I'll probably just give you one question, and it will have 20 parts. And if you miss the first part, the other 19 aren't going to have a chance. So I'll just have to grade one part on your exam. How's that? The teacher course evaluations are due. All right, the final won't be quite like that, but it will maybe be many, many questions, and they'll be broken down like that. Now let's look at using output feedback to try to achieve this S delta. Or you might think of this as being a cascade controller. We are now worried about designing this G sub C. That's the cascade controller that we want with output feedback. And that's all we're doing. We're measuring the output Y and feeding that back with a unity gain. And it's negative. We have negative feedback. G sub C, I'm sorry, G of S, our plant, we have been given in state space form. Our output matrix was 1, 0. We now have S. This was a -1, 0, S plus 1. We need to invert Si minus A and then scale with the input matrix B. Taking the determinant of that matrix, that's now, and dividing by it, we have 1 over S times S plus 1. And what's left are all of the matrices. So now I've inverted that matrix in this step by taking 1 over the determinant and multiplying by the cofactor matrix transposed to give us the matrix that we need for the inverse. If we now multiply that out, we end up with our plant as we did last time. That's still 1 over S times S plus 1. What kind of a system type is that? How do we classify? We have all sorts of ways of describing things, and one of the ways that we've described things so far this semester is a system type. And a type of a system says how many poles we have where? Right at the origin. How many poles do I have right at the origin for this system? This is then a type 1 system. And what do we know behavior-wise that we can achieve with a type 1 system in terms of steady-state error when we have a constant input applied to that system? That's going to give us 0, and we will achieve our steady-state accuracy spec that we wanted if we can close the loop and keep the closed loop system stable with that G sub C in that forward path. We'll achieve this if T of S, which is Y of S over R of S, is stable, where this is our closed loop transfer function. And in this case, T of S is this G sub C G over 1 plus G sub C G. And what would we check for stability? Which of these pieces of T would we be interested in for stability? The numerator piece or the denominator piece? The denominator, and we would want those poles. We said we want the poles of that to be at -4 plus and minus J4. Here is our S-plane. Our plant had a pole at the origin and another pole at -1. And we want, I'm not going to make this maybe distorted a little bit, but this is now -4 plus J4 plus and minus J4. We want our root locus to pass through those triangles. And I hope at this point in the semester you have a pretty good feel for how you could maybe quickly do that. How might you design a controller to achieve your root locus going through those triangles? You could make your life easier by canceling that pole, couldn't you? And now you can simply make a pure two-pole system again, one at the origin and one at -8, so that now this root locus associated with the closed loop system does accomplish what you want. Now you have a controller G sub C of S of K, S plus 1. That was canceling the open loop pole at -1, and you now have a pole of your controller at -8. How do we find K? We just crank the knob, adjust the knob. That's really what we're doing, but we can actually figure out exactly where we need to put that knob and what condition do we use to make that happen. We need the magnitude condition for K, don't we? We need the magnitude of G sub C G, that magnitude equal to 1. We now need G sub C times G. We want that to equal 1 at the appropriate location, which is S delta equal to -4 plus and minus J4. We can cancel that and solve for K. We now can see that K is S times S plus 8, and we want to solve that when S is equal to S delta of -4 plus J4. We now have the magnitude of -4 plus J4. We have 4 plus J4 when we substitute S plus 8 into that. But those two lengths are exactly the same. They have the same real magnitude and imaginary magnitude, which now says that K is 4 squared plus 4 squared, square rooted, squared. So I'm going to quit and not do that, and I now have a gain of 32. 2/16. So now we know that our controller, G sub C, is this 32 S plus 1 over S plus 8. And that's our cascade controller. Why don't I do the full state feedback by hand, and then we'll start doing this in MATLAB, and if we run out of time, I'll do that offline. How's that? So now we found our cascade controller. or the one for output feedback. Let's now look at finding the full state feedback controller. Again, this one is assuming we have all of the state variables, maybe position and velocity, at our disposal. When we are doing a full state feedback, mainly one of the first things we do is need to find where our desired poles. Well, we've already found where they want to be, but we now need to build up this polynomial that has those poles as roots, meaning we need s plus 4 minus j4 times s plus 4 plus j4. Those factors give us poles at minus 4 plus and minus j4. We multiply all of that out, we'll have s squared plus 8s plus 16 plus another 16. There's our desired polynomial that we want to achieve using full state feedback. We started with complex roots, we ended up with real coefficients. How did that happen? Why did we end up with real coefficients and we're not surprised by that, even though we have roots that are complex? What's the reason for that? Our roots appear in complex conjugate pairs, and because of that, that allows us now to end up with real coefficients. We now need to find our closed loop matrix, our closed loop system matrix, using full state feedback. We've done that. That's x dot is equal to ax plus bu, but now u is equal to minus kx plus nr. X dot is now, I do it in a couple of steps, is now this ax minus bkx plus bnr. And we need to now find f. F is a minus bk. Our A matrix was 2 by 2. Our input matrix was 2 by 1. To be compatible, our full state feedback gain matrix needs to be 1 by 2. We can now say that that's the A matrix minus bk for F now becomes 0, 1, minus k1, minus 1, minus k sub 2, which if we now look at the determinant of Si minus F, as a matrix, we now have s squared plus 1 plus k sub 2s plus k sub 1 as our polynomial that has the state variables k1 and k2 floating around in the coefficients. We now need that to equal s squared plus 8s plus 32. That's our desired characteristic polynomial, and we can obtain those values by equating coefficients of the powers of s. If we look at s1, we have 1 plus k sub 2. That's supposed to equal 8. K sub 2 is now 7. The S0 coefficient is K sub 1 now needs to be 32. And now we have then our K matrix is 32 and 7, and all we have left is to find this reference input gain in, and we know the process for doing that. I'll have to pick up at that offline, but I'll complete this and maybe show the comparison of the step responses for these two different designs in MATLAB.